Yes. Hello everyone. So welcome to new session for mass spectrometry. So in your last class in mass spectrometry, we discussed about how to make a fragmentation. So what are fragment ions, how fragment ions are going to be represented, and what type of fissions are going to be observed in mass spectrometry. So almost all three major areas are going to be discussed in your last class of mass spectrometry, especially mass spectrometry class 4. So types of fissions, nothing but we will discuss about what is homolytic, heterolytic as well as hemiheterolysis. Later on we learn about what is fragmentation. So from where we will do fragmentation. Okay, how many molecules are involved in, what type of fragmentations are expected. Then finally we learn how to represent a fragment ion whenever if it is fragmented from a corresponding molecular ion. Okay, so that is about molecular ion as well as fragment ion. So now keep reading types of ions in mass spectrometry. Types of ions. Types of ions involved in mass spectrometry. What are the variable types of ions are involved? With respect to that ions, we are writing a mass specs. Okay, so generally we have molecular ion. Second one is a fragment ion. Molecular ion, fragment ion. Third one is even electron ion. Fourth one is odd electron ion. Even electron ion, odd electron ion. Then one more is there, isotopic ion. Isotopic ion. Next one, multiply charged ion. Multiply charged ion or multiple charged ion means a cation should not carry +1, it may carry +2, +3, +4, x4. That is called multiply charged ion. Otherwise multiple charged ion, both are same. Then molecular ion interaction. Molecular ion interaction ion. Now it is a new ion which is produced by the interaction between molecule as well as molecular ion. Molecular ion produced by molecule. So this already explained. After formation of this molecular ion, this is going to collide with this molecule and forms a new ion that is called molecular ion interaction ion. Okay. Then this is most important one, metastable ion. Metastable ion. Then finally negative charged ion. So these are the 9 types of ions available in mass spectrometry which are responsible to give mass specs. Especially this negative charged ion cannot be represented in mass spec because it is completely having negative charge. Only with negative mass spectrometry we can identify this negative charged ion. So first we are going to discuss individually. So that might help to write a mass specs in mass spectrum if you know these ions clearly. Okay. So first one, molecular ion. Molecular ion. So what is a molecular ion and how molecular ion is going to be developed? What is the use of molecular ion? So what is molecular ion? See, radical cation which is produced by molecule. It is a radical cation which is produced by molecule. By ejecting one of the electron from molecule, you will get a radical cation that is called molecular ion. Initially, this molecule should be in gaseous form. This point is already given. This molecule should be in gaseous form that will lose one electron and forms a radical cation. So radical cation produced by molecule is called molecular ion. Okay. So if you take embedded value of molecular ion is equal to mass of molecule. Suppose I am taking one molecule, I want to determine the weight of that molecule, mass of that molecule. That mass can be determined by embedded value of a molecular ion, which means this is that molecule. This molecule, by applying 7 to 15 electron volts, now you will get radical cation. So once if you calculate embedded value of this molecular ion, this embedded value is equal to mass of this because only one electron difference is observed between molecular ion and molecule. If you neglect that electron, this embedded value and this mass are both are same. So the radical cation produced by molecule is nothing but a molecular ion, right, parallelly. Radical cation produced by molecule is called molecular ion. These points already explained in starting of what is molecular ion, how it is generated, how much amount of energy is required. Okay, so everything is given. That's why given direct point. Embased value of molecular ion is equal to mass of molecule. So write this: types of ions in mass spectrometry: molecular ion, fragment ion, even electron ion, odd electron ion, isotopic peak produced by isotopic ion, then multiply charged ion, molecule, molecular ion, interaction ion, metastable ion, one more is negative charged ion. These are the 9 types of ions are available. Especially you focus on this one. This particular ion cannot represent in positive mass spectrometry. In our spectra, we are not going to represent this one because it is negative charged ion. It can be negligible. It is represented only in negative mass spectrometry. You can ignore this. See, after calculating embased value of a molecular ion, now 2 points you need to remember. If embased value of molecular ion is even or odd, suppose if embased value of molecular ion is odd, that will produce odd number of nitrogens. This point is important. They may give odd number of nitrogens. Means molecule carry odd number. Nitrogens are present within the molecule. If embased value of this molecular ion is odd number, okay, so may carry odd number of nitrogens. Maybe 1 nitrogen, 3 nitrogen, etc. Same point I am repeating. Suppose if embased value of molecular ion is even, okay, that may produce even nitrogens or absence of nitrogens. They may carry 2 nitrogens, 4 nitrogens or 0 nitrogens. This point you remember. So that is a use of embased value of a molecular ion. If molecular ion having a even embased value may carry 0 nitrogens or 2 nitrogens. If they carry odd embased value, they may carry either 1 nitrogen, 3 nitrogen, 5 nitrogen, etc. So with the help of embased value of molecular ion, one can easily identify whether they carry odd number of nitrogens or even number of nitrogens. Okay, then see, every molecular ion need to show molecular ion peak in mass spectrum. So this is a general condition, but this is not mandatory. This point you remember. Every molecular ion need to show molecular ion peak in mass spectrometry. So because most of the organic molecular ions are found to be stable, so we are representing in the form of intensity. So that's why this statement is applicable only for organic molecule. But remember, it is not mandatory. Definitely 100% that molecular ion definitely shows a molecular ion peak is not possible. 100% not possible, but maximum more than 90% of molecules have a tendency to show this molecular ion peak in mass spectrometry. Every molecular ion need to show molecular ion peak in mass spectrometry. So especially, suppose if I take any large molecules or sugars, carbohydrates, terpenoids, steroids, etc. Sugars, so we can expect a very poor molecular ion peak. Sometimes it may be disappear. So that's why this statement is not correct every time. So you can also write like this. There is no possibility of representing molecular ion every time in a mass spectrometry. Every time it is not possible. So this depends upon the stability of molecular ion. We need to represent the peak intensity. But 90% of organic molecules are found to be stable. That's why this statement is applicable, but not for bulk molecule. This point I explained already. Misleadings I explained. So every molecular ion need to show molecular ion peak in mass spectrum, but that is not possible for bulk molecule, large molecules whose stability is very less. Right, parallelly you take down these 3 points. Sometimes even sugar, they doesn't show any kind of molecular ion peak. They may disappear. Not only this one, even for steroids, cholesterol, statins, this point I explained already. You just revise the molecular ion peak and how to represent a molecular ion peak in mass spectrometry, and what are the misleadings. I explained with the impurity, then followed by abundance of heavier isotopes, okay, then followed by interaction peak. Every molecular ion need to show molecular ion peak in mass spectrometry. So generally, suppose this is a molecular ion peak. It is represented by MZ value, and see this is percentage of intensity. Sometimes this peak will be very high, sometimes it may be very low. Sometimes it may be disappear like this. Maybe lower height, maybe higher height. So this height depends on this stability. This is molecular ion peak. So this height depends upon the stability. So finally we can say, if I take any organic molecule, molecular ion is unstable. It is found to be unstable. Initially organic molecule is even electron species. After losing electron, it forms a odd electron. Odd electron is unstable. It is unstable, produce paramagnetic character. It will give paramagnetic character. So indirectly I am saying that if any organic molecule lose electron, forms a molecular ion. The molecular ion formed by any organic molecule, it is found to be paramagnetic in nature. So organic molecules shows a paramagnetic molecular ion. This point given in GATE exam. In GATE examination, this statement is given directly. Organic molecule, molecular ion is unstable. Initially I am taking one organic molecule. This organic molecule losing one electron and forms a radical cation. So this is paramagnetic I am saying. Initially gaseous state molecule is found to be even electron species. Now it becomes a R electron species. So this is found to be paramagnetic in nature. So this is especially for organic molecular ions. Organic molecular ions are odd electron species. Initially stable, unstable undergo fragmentation rapidly. Due to instability, this fragment or this particular molecular ion may undergo further fragmentation. It is paramagnetic in nature due to one electron. And finally, inorganic molecules are inorganic molecular ions are diamagnetic in nature. They are diamagnetic, inorganic, but organic is paramagnetic. You compare these two molecular ions. Inorganic unstable becomes stable, means paramagnetic to dia. But when you take any organic molecule even. Now after losing electron forms odd, means stable to unstable. So that's why organic molecules effectively undergo fragmentation as compared to inorganic molecules. So that is about molecular ion. In types of ions, we discussed what is a molecular ion. that is about molecular ion, that is first ion is over. Next one, fragment ion. How many types of ions we are discussing in mass spectrometry? With the help of that ions, one can easily identify a peak with respect to corresponding ions, fragment ion. So, the ion produced by fragmentation of molecular ion or daughter ion. Means every time don't think that this fragment ion produced by molecular ion. Molecular ion after producing one of the fragment ion, that fragment ion one more time it will give one more fragment. That fragment will give one more fragment. So that is successive process. Yesterday given with an embedded value 58, then followed by 43, 29, 15 like that. So every time molecular ion will not give all kind of ions. Okay, every time molecular ion responsible to give one ion. That ion undergo further fragmentation. Regularly it is keep on progressing to give variable ions that will give structural information. So I can say that fragment ions produced by molecular ion as well as daughter ion. Okay, so this fragment ion, always remember fragment ion having lower embedded value. They are having low embedded value than molecular ion. If I take molecular ion and fragment ion having lowest embedded value than molecular ion. So always they are represented left side of molecular ion peak. Always fragment ions are represented by left side of molecular ion. Right side of molecular ion different peaks are represented, but fragment ions always represented left side of molecular ion, because fragment ions having lowest embedded value as compared to molecular ion. Suppose if I take pentane or I take butane 58, then 43, 29, 15. So 43 is a top value, initially 58 to 43, 15 difference, then 29, 15. So regularly values are decreasing. So I can say molecular ion having highest value, later on values will be get decreases. So I can say that after molecular ion identification, if any value is lower than molecular ion, that all are coming from the molecular ion only, not even directly. Indirectly also possible. Indirectly means from daughter to daughter, grandfather to father, father to children. So this is possible here. Okay. So fragment ion always produced by molecular ion. It is same way that molecular ion also give a daughter ion. The daughter ion also responsible to give one more fragment ions clearly. So I can say that always represented by left side of molecular ion. So I can represent like this. This is embedded value, here percentage of intensity. This is molecular ion. And whatever ions are present here, this all ions or peaks are belong to daughter. Okay. This daughter may come directly from molecular ion, or this daughter may also come from this. See, this is responsible to give this one. This is responsible to give this one. One by one. Molecular ion will give this one. Then this particular fragment will give this one. This fragment will give this one. So it is a successive process. Don't think that molecular ion will give these three at a time. On the spot it is not possible, but initially these three are produced by molecular ion only, not directly. So these three are coming from molecular ion, but initially molecular ion will give this peak, first fragmentation, next fragmentation, this will give this one, this will give this one, but all are coming from molecular ion only, not directly. Okay, so we can determine with the help of fragment ion, we can determine nature of fragment. We can determine nature of fragment. So means what type of fragment is present, whether it is methyl or it may be ethyl or it may be isopropyl, like that. What type of cation is present within the fragment, that can be determined based on embedded value. Okay, formyl group CO plus, okay, and even you can take a fragment which is producing double bond like this. You can write any fragment here now like this. So this kind of fragments, if they are present within the molecule, that fragments will be removed out. So we can identify the structure of fragment within the molecule. So I can explain nature of fragment. Okay. So once if you explain nature of fragment, that is used to determine structure of molecular ion. We can determine structure of molecular ion. With the help of fragment ion, one can determine structure of molecular ion. And we can also explain connectivity. Connectivity of fragment in molecular ion. Connectivity fragment in molecular ion. Only one point you remember. That is, with the help of these fragment ions, I can explain. With the help of this fragment ion, explain what type of fragment is present. What is the structure of fragment? What is the nature of fragment? And what is the structure of parent? One over other connectivity. With the help of one connectivity to other connectivity, a long chain, branched chain, or any aromatic, anti-aromatic, every molecule can be determined by using this connectivity. Okay. So fragment ions can be easily represented by using this particular process. Maybe fragment ion is a base peak. I will explain what is base peak. Maybe it may be a base peak or may not. May not be a base peak. So don't think always fragment ion is not a base peak. May not be a base peak, may be a base peak. So what is a base peak? The peak which having highest intensity. See in this one, molecular ion having highest intensity, this is a base peak. Sometimes if I take a spectra where intensity of fragment is very high. See, this is a molecular ion. This all are embedded value, percentage of intensity. Now this is molecular ion. And if I take remaining these three peaks, okay, so this is daughter ions. Now daughter ions in which one of the peak of daughter having high intensity as compared to parent. So now this is belongs to base peak. Now here see all daughters having lowest intensity as compared to molecular ion. Now molecular ion is a base peak, but here fragment ion is a base peak. So I can say one point that fragment ion may be more stable than molecular ion. Sometimes molecular ion is more stable as compared to fragment ion. That depends upon the stability. It is not depends upon the molecule. It depends upon the stability of a corresponding cation, corresponding radical. Two things we need to consider, because after getting radical cation, this will undergo fragmentation that may give only cations, cation, but it is a radical cation. But maximum cases, molecular ion peak intensity less than fragment ions, because in most of the organic molecules, radical cations are unstable as compared to corresponding fragments. Fragments are even electrons, but this is odd electron. Okay, so that is about fragment ions. Here key points are, what is the use of fragment ions in mass spectrometry? That point remember. Fragment ions always represented left side of molecular ion. This fragment ions always having lowest embedded value than molecular ion. This fragment ions generally used to determine the structure of this. With the help of this, I can determine the corresponding connectivity within the molecule. I can also explain overall structure of a corresponding molecular ion. So that is use of fragment ion. Fragment ions also explain their stabilities. May be base peak or may not be base peak. So that is about fragment ion as well as molecular ion. Next two ions we are going to discuss at a time, that is even electron ion as well as odd electron ion. These two ions we are going to discuss at a time. So fragment ion, molecular ion both are over to represent in mass spectrometry. Next is so third one and fourth one we are going to discuss at a time, even electron ion, odd electron ion. So 3 and 4 ions will be discussed at a time, even electron ion and odd electron ion. So what is odd electron ion? So I am taking a positive charged species having odd number of electrons. So they are having only electrons. Just count the total number of electrons. If that electrons are odd number, that is called odd electron ion. So these definitions are very, very important. Try to listen carefully. If any molecule having or any fragment having positive charge, and if they carry odd number of electrons, may consist 5 electrons, 7 electrons, 9 electron, level 13, that is nothing but odd electron ion. This is known as odd electron ion. Positive charge species having odd number of electrons is called odd electron ion. So better example, see, suppose if I take CH4 radical cation, here one electron is present, so it is an odd electron ion. Okay. Suppose if I take benzene and here also radical cation, so it is also odd electron ion. Odd electron nothing but if they carry 7, 9, level 13, 15, 5, 3, that electrons, one independent electron is present, it is not paid. So many examples you can write. Most of the molecular ions belongs to this case. See, this is molecular ion. So every time remember, all molecular ions, especially coming from organic molecules, belongs to odd electron ion. Try to listen carefully. It is very, very important topic. If you understand this one, you can understand rules regarding mass spectrometry. Positive charge species having odd number of electrons, nothing but odd electron ion. OEI. This is called odd electron ion. Remember, whenever if I say the word odd electron ion, they carry odd number of electrons. Only odd number of electrons, don't count m by z value. Don't work out mass. Only electrons we are counting. Based on the number of electrons, I am saying it is a odd electron species. They carry odd number of electrons. Now, I am showing one more. Positive charge species having even number of electrons. If any positive charge species having even number of electrons, that is called even electron ion, EEI. Positive charge species having odd number of electrons is odd electron ion. Positive charge species having even number of electrons is called even electron ion. Even electron ion nothing but they carry even number of electrons. So whenever if I say the word electrons, count electrons only. Don't count m by z value. M by z value is different. Type of ion is different. Here I am writing a type of ion, only ion. Based on the electrons I am saying the ion. Even electron ion carry even number of electrons, not even mass. Mass is different, m by z value is different. Okay. Suppose if I take CS3 plus, this is an even electron ion. And here see, there is no independent electron first of all. Ethyl carbocation, and I can write isopropyl carbocation, then I can write phenyl carbocation like this. So in this all cases carry even number of electrons. Suppose one of the example I will show, a carbocation, methyl carbocation, here I am writing positive charge. If you count total number of electrons like this, 1, 2, 3, 4, 5, 6, 6 electrons are present. So I can say it is a even electron, 6 electron. And one more example, ethyl carbocation I am taking. Ethyl carry 2 hydrogens of the carbocation, adjacent one more methyl group is present. If you count total number of electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they carry 12 electrons, they carry 6 electrons. So back to back, if you keep on counting every molecule, only cation electrons we need to count. Don't count embedded value. You may not get same embedded value. Embedded value is different, type of ion different. See the name, even electron ion means ion carry even number of electrons. Ion carry odd number of electrons. We are classifying based on number of electrons only. We are not classifying based on embedded value. Embedded value is different. Nature of ion is different. Ions are two types, even electron ion and odd electron ion. So I will write in two different forms, even electron, odd electron species. Even electron species carry even number of electrons, odd electron species carry odd number of electrons. That's it. So one more example I will show to identify even electron ion clearly. Suppose see, this is a carbocation having embedded value 15. This is embedded value, remember. This is embedded value. Now, one more ion I am writing, this is called ethyl carbocation, same. This is 29. And if I write isopropyl, CH3 taken 2 times, CH plus, your embedded value is 43. Okay, 15, 29, 43. Mass number is odd. Here mass number is odd. Don't think it is a odd electron ion. Remember, these all ions are even electron ion having a odd mass, odd embedded value. So remember, don't think that even electron ion having a even embedded value. That is wrong statement. I will show one technique how to identify. But remember, there is no relation between even electron ion and odd embedded value. So if cation may be even electron ion, may give odd embedded value. That is possible. So don't think that only with the help of mass we are writing this particular cations. That is wrong statement. Only with the help of embedded value we are not writing these cations. We are writing based on electrons. See, this representation based on number of electrons. This representation based on embedded value only. So one key point over here, just to concentrate. See, if molecular ion having presence of nitrogen, if molecular ion having presence of odd nitrogens, so here you better write odd number of nitrogens, odd nitrogens. So then see, even electron ion produce even embedded value. Okay, even electron will give even embedded value. You remember this point, even electron, even embedded. Here see, even electron, odd embedded, different. But here see, in the same way, odd electron ion will give odd embedded value. This point is very, very important. This is applicable when nitrogens are in odd number in a given molecule. This is important for CSR examination. From here onwards, be careful. Nitrogen rule is going to come. That may helps in this part. If molecular ion having presence of odd number of nitrogens, if any molecular ion having odd number of nitrogens, whose embedded value is also odd, it is an odd electron definitely. Okay, so if it is odd embedded value, even embedded value. Okay, this point you remember. I will give an example. See, this is pyridine. This is radical cation. Every carbon 12, every nitrogen 14. Just you add 14 and every hydrogen 1. So 1, 2, 3, 4, 5, 6. Total 5 carbons, 1 nitrogen, total 6. So add 5 hydrogen. So finally here only 1 electron which is present in the form of independent radical. I can say it is a odd electron ion. It is a odd electron ion. Only 1 electron. Blindly remember when 1 electron is an odd electron ion. And if you count the embedded value of this species is 79. It is 79. Just remember, even nitrogen also assume as carbon. And at last every nitrogen just add 2. 1, 2, 3, 4, 5, 6. 6 into 12. 72. 72 plus 2, 74. 75, 76, 77, 78, 79. Now see, odd electron ion, odd Mbz value. Both are odd numbers. Then how many nitrogens are present? Odd number of nitrogens. If odd number of nitrogens are present, odd electron ion will give odd Mbz value. This point you remember. Odd electron ion will give odd Mbz value if they carry odd number of electrons. And one more example I will show. This is nitrogen. It is a molecular ion, radical cation. Radical cation. So if you compare every carbon, every nitrogen, 12 and 14 we need to add. But while counting, just assume that nitrogen is also carbon. 12 plus 12, 24. 24 plus 2, 26. 28 and this is 31. So I can say Mbz value is 31. Mbz value 31, but only one independent electron is present. So I can say it is odd electron ion. That's it. If only one electron is not participating, that is called odd electron ion. And one more example I will show. See, this is NH2 plus. Count Mbz value. Now it is a even electron ion. There is no independent electron, even electron ion. So 12 plus 14, 26. 26 plus 4, it is 30. So now Mbz value is 30. See, even electron ion, even Mbz value. Even. This even, this is also even. So I can say this statement is matching. See, even electron ion giving even Mbz value. Odd electron is giving odd Mbz value. So this point applicable when nitrogens are odd number. Only when they present odd number. 1 nitrogen, 3 nitrogen. On that time odd to odd, even to even. This point you need to remember. So same statement, almost all same. See, if molecular ion having, see, absence of odd nitrogens. If odd number of nitrogens are absent, then odd electron ion is produce even Mbz value. They will give even Mbz value. Even electron ion will produce odd Mbz value. Even electron, odd electron, Mbz values are completely varies. Different, quite different here. See, in this case, even to even, odd to odd. Even electron, even Mbz value. Odd electron, odd Mbz value. But in this case, odd electron ion is giving a even Mbz value. Even electron ion is giving a odd Mbz value. This is applicable strictly for ion having no nitrogens. Ion having no nitrogens or even nitrogens. Here they may carry odd nitrogens. 1 nitrogen, 3 nitrogens, like that. Even number of nitrogens. And this is odd nitrogens or absence of nitrogens. Okay. Suppose one of the best examples, see, this is a carbocation, methyl carbocation. It is even electron ion. Even electron ion, and see the Mbz value. Mbz value is 15. Odd number. Odd even. Even electron, odd mass. Same example what I given just now. So this is ethyl carbocation, even electron ion, Mbz value is Mbz value 29. And if I take isopropyl, 43, Mbz value is 43. Just count this, and it is even electron ion. If you know this clearly, fragmentation mode is very easy. Suppose if I take benzene, see, here I am writing carbocation. So Mbz value is 77. 77 means it is a even electron ion. There is no nitrogen, but if you see this species, it is even electron, no nitrogen, now odd mass. Odd Mbz, even electron ion. And if I take phenyl carbocation, see, this is radical, this one. Mbz value will be 78. 78, now one independent electron is there, even electron ion. So this kind of examples are very high in number as compared to this, because here nitrogen is mandatory. Okay, so here if I take this one, cyclopropenyl cation, aromatic skeleton. So MZ value 1, 2, 3, 36, 37, 38, 39. So now MZ value is 39. 39, there is no nitrogen, so I can say, is it even electron ion or not? Yes, it is even electron ion. Now, and if I take phenyl, which is responsible to give double bond, triple bond, in last class I explained. MZ value is 51. See, 1, 2, 3, 4, 48 plus 3, 51. Now, MZ value is 51. MZ value 51. Now it is a even electron ion. Like this you can take many examples. If you remember this statement clearly, you can attempt any kind of question. What type of ion and what type of its MZ value. So now play with MZ value. Every time you try to remember MZ value and type of ion. Type of ion, MZ value, both are not same. Both are different. So this is called odd MZ. Odd mass, even mass. This is odd mass, odd mass, odd mass, odd mass, even mass, odd mass like that. Okay. So this mass is different, here type of ion is different. So 2 points remember, when odd number of nitrogens are there, even to even, odd to odd. When even number of nitrogens or no nitrogens are present, even to odd to even. That's it. So I will give some fragments, try to calculate MZ value and say the type of ion. Just work out and see the ion. Okay. This is a formyl cation. Here you write down MZ value. Here you write down type of ion. Be careful, type of ion. 2. Left side fragment, 2 columns you write down. What is MZ value? What is its nature of ion? Either even electron ion or odd. Every carbon 12, every oxygen 16. Otherwise, just assume that oxygen is also a carbon. Carbon, then every oxygen add 4. Every nitrogen add 2. 12 plus 12, 24. 24 plus 4, 28. And this is 29. MZ value is 29. And it is even electron ion. Clear? Even electron ion. Why it is even electron ion? Because there is no nitrogen. See, any independent electron is there? No, no independent electron. So I can say this one. Now, this is formyl, now it is acyl. Acyl. See the difference? And if you compare these two, just add 14. 12 plus 2 hydrogens, that becomes 14. So add 14 to this one. Then you will get a specified value. That value will show the corresponding MZ value and fragment ion nature. 1, 2, 3, 36 plus this 4. 40 plus 3, 43. So I can say 43. 43 is a even electron ion. See, there is no independent electron. This we are writing based on number of electrons. Acyl. So, if you write this benzoyl cation, so this is 105, MZ value 105, and here it is, there is no independent electron, now it is a even electron ion. Even electron ion. Okay. Now, if I take toluene, this is toluene. Toluene Mbz value is 91 and this is even electron ion. See on which basis I am saying even electron? Based on the number of electrons. This is based on the mass, number of carbons, number of hydrogens, etc. Okay. Suppose if I take a oxygen CH2 double bond O and here it is H and here positive charge is present, then what will be the Mbz value of this corresponding species? 12, every oxygen is 16, every nitrogen 14, every carbon 12. Otherwise, every oxygen just assume that carbon. 12 plus 12, 24. 24 plus 4, 28. 29, 30, 31. So now it is 31. 31. Now it is even electron ion. There is no nitrogen, but it is even electron ion. Like that we can write many examples. Okay. So that is about some selective examples of even electron and their corresponding Mbz values. Okay. So if you compare these two ions, even electron ions are highly stable. They are highly stable over odd electron ions. Even and odd if you compare, even is more stable than odd electron ions. Okay. So if you see, suppose this is the energy levels of corresponding ions. So this is called odd electron ion. This is odd electron ion and this is called even electron ion. Even electron ion having a paired arrangement of electrons. This is even electron ion. Whenever if I say the word odd electron having one unpaired electron, one non-bonding electron is present. But what about here? There is a paired arrangement of electrons are there. Paired electrons are present, but here unpaired electron is present. So, due to presence of this unpaired electron, it is found to be unstable. Odd electron is unstable, but this is found to be stable. Always even electron is more stable than odd electron. So, why even electron is more stable? Every electronic energy level having a paired arrangement of electrons here. But in this case, unpaired electron arrangement is present. At least one non-bonding electron is present, that becomes unstable in a system. Even electron ions are highly stable as compared to odd electron ions due to presence of unpaired electron in odd electron ion. Okay. So, if I take most of the molecules produce even electron ions. Only even electron ions are going to be produced. Okay, they won't produce odd electron ion because even electron ions are stable, but initially that molecule or a fragment is unstable. That's why when competition comes, majority of molecules or most of the molecules want to deliver even electron ions only. They won't give more number of odd electron ions. So you try to remember this point. Most of the molecules, if competition comes, whether they are giving even electron and odd electron, remember they will give even electron ions only. Suppose if it is giving any odd electron ion, that is undergo further fragmentation. So, but what happens, see, if molecule is giving even electron ion, that fragment is found to be stable. But if any molecule is giving odd electron ion, that is giving more structural information. So, I can say that odd electron ion produce more structural information. If you want to get any structural information, that structural information produced by odd electron only, not even electron. Even electron will give less information about structure of a molecule, but odd electron will give more information about the structure. But even electron is more stable than odd. Okay? Even electron is diamagnetic, Odd electron is paramagnetic in nature. These two ions you need to remember. With nitrogen, with one nitrogen, even, odd. Without nitrogen, even, odd, even. Even electron more stable. Odd electron unstable due to arrangement of electrons. Properly arranged, improperly arranged. Even electron, majority of molecules. Suppose see one molecule undergoing fragmentation. If you take butane, we are getting 58, 43, 57, 58, 43, 29, 15. All are even electron ions only. So I can say that if any molecule undergo fragmentation after formation of molecular ion, maximum they will deliver even electron ions only in mass spectrum. Very few will give odd number of electron consisting ion. But this ion, if it is obtained, they undergo further fragmentation more effectively. So when this will give more information about the structure, this will give less information about the structure. So this point also given in GATE exam. In GATE examination as well as CSR, they are asking about isotopic peaks as well as fragmentation base peak questions are common. But in GATE, this kind of theoretical questions they are asking. So what is the most common ion liberated by an organic molecule? Even electron. So which ion will give more information about structure? Structural information given by odd electron ion only. So one example I will show. Just see, this is one radical cation. This is on electronic impact. 70 electron volts, there is a formation of a radical cation. So now this is a odd electron ion. So no need to calculate implicit value because one electron is independently exists. Now if you apply retro Diels order reaction, further fragmentation, so you may get this one. So you will get double bond. Yesterday given a double bond radical cation. Now see, this is neutral. Forget about this. This is neutral. Then what about this one? This is one more odd electron ion. One independent electron is there. When you get any odd electron ion, you will get one more fragment. That fragment is unstable. It will undergo further fragmentation. That is further fragmentation that is responsible to give more information about the structure. So that is the advantage of getting odd electron ion. So if you go through left to right, now we are getting a ring formations. So most commonly, if you compare odd electron and even electron, getting odd electron giving more information. Because it is unstable, if any choice is there, undergo further fragmentation. Okay, that will give more information to determine the complete structure of this original molecule. So that is about odd electron ion and even electron ion. Two key points you need to remember. What is odd electron ion and what is even electron ion? Odd electron ion depends on odd number of electrons. Even electron ion depends on even number of electrons. And if you compare with number of nitrogens, odd nitrogens, odd to odd, even to even. Even nitrogens are no nitrogen, odd to even to odd. So some fragment embedded value, nature of ion, both are explained. So this is very important aspect if you want to apply the rules in fragmentation mode. So this you practice clearly. Means what is even electron and what is embedded value. Even electron ion is different, embedded value is different. Don't compare both. If you want to compare, reference is nitrogen. Even electron ion carry even number of electrons only. Odd electron ion carry odd number of electrons only. That's it. Only the 2 points you need to fix in your mind. So 3 types of ions we discussed, especially 4 I think so. because first we learn about what is a molecular ion, later daughter ion, nothing but fragment ions. Later we discussed even electron ion as well as odd electron ion. Total 4 types of ions we discussed. So your key points is how to calculate even electron ion and how to identify their M/Z value. Nitrogen is a reference between them. Next, fifth one. Yeah, this is most important one. Isotopic ion. Isotopic ion, otherwise we can say isotopic peak. Isotopic peak produced by isotopic ion itself. Okay, so what are isotopes? How these isotopic peaks are going to be helpful, and what is their relative abundance and natural abundance? Everything will be discussed in this concept. Isotopic peak. So, in nature, if I take any element, many elements exist in mixture of isotope. Exist in mixture of isotopic form. So what is the meaning of isotope? Same atomic number but different in their mass number. So in nature, generally, if you take many elements in periodic table, many elements having more than one isotopes are there. So that is called mixture of isotopes. Okay. So the isotope, if any isotope having more abundance, the isotope having more abundance is known as generally common isotope. Common isotope. This is also called lighter isotope. This point you remember. Lighter isotope and heavier isotope. Common isotope nothing but, suppose one element, if you take that element having 10 isotopes in nature, when you extract from the nature, that element have a tendency to give 10 isotopes, in which all isotopes not are easily extracted from the nature with same ratio. Means availability of corresponding element in isotopic form is differ. Suppose out of 10 isotopes of one element, one isotope having a maximum abundance, means if you extract from the nature, that is available. Very easily it is available. That is called lighter isotope. So commonly we are extracting, that's why it is called common isotope. Common isotope nothing but most available, most abundant isotope of corresponding element is called common isotope. Okay. So every element having more than one isotope, in which one of the isotope having most availability, that is called common isotope. This isotope also called lighter isotope. So lighter isotope having heavier abundance, common abundance, easily extractable. Okay. So then one more, the isotope having less abundance. If any isotope having less abundance, generally that is known as heavier isotope. This is also called uncommon isotope. This is uncommon isotope. This is called common isotope. Common isotope is commonly available. This isotope is not commonly available. That's why it is called uncommon isotope. This is also called heavier isotope. So means weight will be very high, mass will be very high. So due to higher masses, availability is very less. This is most common, this is less common. Suppose if you want to calculate M/Z value of any element present in any compound or any molecule, so we need to consider only heavier isotope or lighter isotope. Consider only lighter isotope. While calculating embedded value of any element, consider lighter isotope or common isotope only. Don't consider heavier isotope, because heavier isotope extraction is very poor. So few elements are there having monoisotopic in nature. Few elements are monoisotopic in nature. So what is the meaning of monoisotope? Monoisotope means they don't exhibit any kind of isotopes. They exist uniquely. Okay, so best example F19, P31 and here iodine 127. So these isotopes not possible to extract more than one form. So they are called monoisotopic in nature. Suppose if these elements are given, always add 19, 31 and 127 only. There is no other isotopes are extracted for this element. They are called monoisotopic in nature. This is called heavier isotope and this is lighter isotope. So in calculation of embedded value of any sample molecule, so we need to take mass of a lighter isotope of corresponding elements. Okay. Suppose if I take carbon lighter isotope 12 and this is heavier isotope. Lighter, heavier. Hydrogen 1 and here there is 2 and 3 will be there. This is called heavier isotopes. Nitrogen 14. Nitrogen also exhibits in the form of 15. Oxygen 16 and here oxygen also exhibits in the form of 17 and 18. Then we can also go for 32 sulfur, 33, 34. Chlorine 35. Then we can also exhibit chlorine 37. Chlorine 37. So these all are lighter isotopes. These all are lighter isotopes and these all are heavier isotope corresponding elements. Okay. This is heavier isotopes. This is lighter isotopes. So remember this. Lighter isotopes used in calculation of embedded value. Don't use this one, because their availability in combined form is very poor. That's why we can ignore this one. Okay. Lighter isotopes used in calculation of embedded value. Only this will be used in calculation of embedded. right? So lighter isotope, these are the most common lighter isotope, and this is heavier isotope. Suppose if you take carbon, generally two isotopic forms are expected, 12 and 13, right? So C12, if I take, whose availability is nearly 98.9% in nature, but if I take C13, whose availability is only 1.1 percentage. So C12 percentage is very poor as compared to C13. So while extracting the element carbon, this is most abundant and this is less abundant. So naturally, while calculating, percentage of lighter isotope is taken as a 100%. Relatively, availability of heavier isotope is taken as relative abundance. So this 1.11 we are writing based on this lighter isotope only. So this is called relative abundance and this is natural abundance. So if you assume that this 98.9% is a 100%, then what is the percentage of C13 with respect to this? That is called relative abundance. Now two abundance will be there. Okay. So by considering lighter isotope abundance 100%, by considering lighter isotope abundance as 100%, okay, heavier isotope is calculated. Heavier isotope abundance is calculated. Heavier isotope abundance is calculated. This is called relative abundance. This is relative abundance. By considering lighter isotope abundance as 100%. So whatever abundance is available for this lighter, that should be taken as 100%. Based on this abundance is calculated. That is called relative abundance. This is assumed as 100%. This is assumed as 100%, and this percentage is going to be increased as 1.11 percentage. That is called, this is relative abundance. This is absolute abundance. This is natural abundance. These two are natural abundance. So this abundance and this abundance is called, especially this one, this is called relative abundance. So every time lighter isotope percentage is taken as 100%. And if you compare the percentage of heavier isotope with respect to this 100%, that is called relative abundance. So your 2 points are very, very important. What is natural abundance and relative abundance? So this time one bromine question is given based on this isotopic ratio only. Okay. Suppose if I take carbon, so C12 is taken as 100%. C12 is taken as 100%. C12 percentage is 100. Okay. And if I take C13, with respect to this, what is abundance of C13? C13 abundance is 1.11 percentage. This is the natural abundance of C12. Okay. So this is a reference every time. Lighter isotope, with respect to lighter isotope, what is abundance of heavier in nature? 1.11. So carbon abundance is 1.11. So here we need to maintain some percentage. C12 100% and here C13. So this should be taken as 1.11. 1.11. Okay. Hydrogen 1H1, it is taken as 100%. It is 100%. This is lighter and this is heavier. Okay. Hydrogen, that is H2, deuterium, otherwise H2 isotope. So 0.016 percentage. 0.016 percentage is to abundance. Okay. So then followed by nitrogen. Nitrogen 14, it is taken as 100% abundance. So nitrogen 15, abundance is 0.38 percentage. This you need to remember. No other alternative. So this is lighter isotope abundance. Right side columns are belongs to heavier isotope abundance. Lighter isotope always taken as 100%. Heavier isotope, its heavier isotope percentage I am giving now. Okay. Suppose if I take oxygen 16, O16 is 100%, O17 is 0.04 percentage, and here one more isotope is there for oxygen, O18, whose abundance is 0.2%. So these all are heavier isotopes. There is no heavier isotope of carbon 14. Okay, so this is only for carbon, this is only for hydrogen, and this is for nitrogen, and this is for oxygen. Remember, oxygen abundance is C12, hydrogen, nitrogen, and this is this. Okay, sulfur 32. 32 is taken as a lighter isotope, 100%. 33, S33, whose abundance is 0.78 percentage, and S34, so whose abundance is 4.4. These values you need to remember. Lighter abundance availability 100%. With respect to this, other abundance availability is this. So chlorine 35, lighter isotope, 100% is taken, and chlorine 37, so whose abundance is 32.5. This you need to remember. Chlorine and bromine. So bromine 79, that should be taken as 100%. Bromine 81, that is taken as 98%. See this isotope. Only bromine is the element whose abundance is almost all equal to lighter isotope. See, chlorine 35, 37. This is 37 and this is 35. Lighter and heavier. Difference is plus 2. And here also difference is plus 2. So there is no plus 1 isotope from bromine. Bromine there is no plus 1. Only plus 2 isotopes are there. But see, this oxygen having plus 1. Nitrogen also having plus 1. Sulfur having also plus 1. See, 32, 33. Plus 1 difference. Like that. Suppose if I take carbon monoxide. What are the lighter isotopes of carbon monoxide? C12, O16. Okay, so this is taken as a molecular ion. Now, this carbon should be taken as C13, O16. So here difference is 12 plus 16, 28. Now it is 21. So this is M plus 1. And even this is taken as C12, O17. C12, O17, it is also M plus 1. So here value, molecular ion lighter isotope value is 29. See, this is 16 plus this 28, and here 13 plus 16. So now here value is 29. Now one more possibility, I can write carbon monoxide with, here this is 12. You write plus 2 difference is required. So this is 13 and this is 17, plus 2 difference. So otherwise we can also write this is 12. This is 12 and this is 18. O18 also we can write. Then this is 13 and this is one more heavier value should be written. See, this is 12, 18, 13, 17. 13, 17, it becomes a heavier value, 30. So value becomes 30 here. So this is 30, here also 30. Means difference will be very high. So the difference between lighter isotope and this one is plus 2. So I can say it is M plus 2. So here difference is 30. Suppose one more I can write, this is 13 and this is 18. So here this is called M plus 3 peak, this is called 31. So these all are isotopic peaks only. So these values you need to remember. So this is M plus 1 peak, M plus 2 peak, M plus 3 peak. These all are called isotopic peaks. This is isotopic peak. So chlorine value 32.5, 1 by third, and this is almost all 1:1 ratio. Molecular and peak and bromine, if isotopic peak, this question, the bromine is very, very important. 1781, 100%, 98% C, 98%. So means lighter isotope and heavier isotope almost all same intensity. So that's why when molecular and peak, isotopic peaks having almost all same. On that time, that molecule becomes consisting at least one bromine. Suppose if it is 1 by third, only one chlorine, 32.5. So one binomial expansion formula is there to identify the intensity of these peaks. A plus B to the power of n. So how many number of bromines are present, that will be added here. 1:1 ratio, 1:3 ratio, 1:1 like that. So this you need to remember. Carbon, lighter isotope 98.9% taken as 100%. We are assuming as 100%. With relative this, 1.1 percentage is assumed as 1.11. Actually it is 1.1 only, but if you assume as this as 100%, this becomes 1.11. Carbon is most important. First you remember carbon 1.11. With the help of C13 1.11, I can determine how many number of carbons present in a given sample. This is very, very important value. Carbon 1.11, M plus 1 peak. M plus 1 peak, carbon is most important because see, here 12 plus 1 difference is what? Only 1. So now these all are sharing their contribution for M plus 1 peak. Now these all are sharing their contribution in M plus 2 peak. These all are M plus 2, these all are M plus 2. In M plus 2 peak, oxygen contribution is 0.2, sulfur contribution is 4.4. So chlorine is 32.5, here 98%. So based on the contributing elements, we can identify what type of element is present in given organic sample. So if I take M plus 1 peak, in M plus 1 peak 1.1%, but see 0.016, 0.3, 0.04, 0.78, almost all maximum carbon and sulfur is contributing for the intensity of M plus 1 peak. So that's why we can guess number of carbons in a given molecule if this contribution is completely neglected. See, if this contribution, if I neglect clearly, M plus 1 contribution if I neglect clearly. So this is M plus 2, remember, don't write in this column. Here one column you write empty like this. This column is empty. So on this side we are writing this one because it is M plus 1 peak and this is M plus 2. Chlorine bromine will give M plus 2 only. See, isotopic peaks are represented by m plus x. Here it is represented by m plus x. What is x indicates? Difference between lighter isotope values and heavier isotope value. So here x is the difference between, it is difference between lighter and heavier isotopes. So lighter and heavier isotopes, if they are added in a given sample, are present. Okay, so added, otherwise you write presence of lighter isotope or heavier isotope, that value may be changes. M plus 1 peak, M plus 2 peak, M plus 3 peak means isotopic peaks only. So in mass spectrometry, isotopic peaks represented right side of molecular end. They are represented right side of molecular end peak. Once if you calculate molecular end peak, exactly right side isotopic peaks are represented with M plus x. X nothing but difference between molecular ion and heavier isotope difference. M is nothing but a molecular ion with lighter isotope. X is nothing but a difference in their mass by adding some heavier elements or heavier isotopes. So here commonly it is represented by molecular ion peaks are represented by M plus 1, M plus 2, even I can take M plus 3, like this we can write. So this is complete representation of a isotopic peak. See, this is molecular ion peak, this is second peak, third peak, and this is fourth peak. So I can say it is M plus 1, here it is M plus 2, third difference M plus 3, and this is M plus 4. So this peaks exactly embedded value percentage. This is called isotopic peaks. This speaks information about what type of isotopes are present in that one. Especially M plus 1 peak gives information about carbon. M plus 2 peak gives information about chlorine and bromine. So this point is very, very important. M plus 2 and M plus 1. So from this only, this year in CSR examination, 1 4 marks question is given with bromines. Suppose one example I will give, carbon monoxide. So if I take carbon monoxide, this is a lighter isotope, molecular ion with C12O16. This is your molecular ion, this one, CO. Here embedded value, percentage of intensity. Now with respect to this, this is 28 to 29. This is 28, value is 28 peak, this one. Now M plus 1, 28 plus 1, 28 plus 2, 28 plus 3. So I can write three different peaks with a different abundance. So I can say CO, three possibilities we can write, 2, 13, 16, 12, 17. So this I am saying 29 peak. Just roughly I am writing, this is 29. This is called M plus 1 peak. In M plus 1 peak, these two ions availability is present. Availability is there. Now this is M plus 2 peak. This is M plus 2. M plus 2, embedded value is how much? 30. Now this becomes a M plus 3. M plus 3 abundance with respect to this one. So these three peaks additionally after molecular and lighter isotope, these three peaks we are getting, these three peaks are belongs to isotopic peaks whose availability is very poor. Okay, so these are represented exactly right side of molecular ion. This is your molecular ion. Molecular ion always carry lighter isotopes only. With respect to molecular ion, lighter isotope abundance is taken as 100%. Based on that, heavier isotope percentage will be calculated in isotopic peaks. So that is the use of isotopic ions. So that is about few types of ions. Especially we discussed molecular ion, fragment ion, then even electron ion, corresponding MBZ value calculation with nitrogen, without nitrogen. Then odd electron ion, MBZ calculation with nitrogen, without nitrogen, then followed by isotopic ions. So in isotopic ions, generally isotopes are helpful to determine M+1, M+2, M+3 peak. Especially these isotopic peaks, in your examination only M+2 peak and M+1 peak is most important. Elements such as chlorine, bromine, carbon, okay, whose percentage of abundance you need to remember. Chlorine 32.5, bromine M+2 peak is 98%, oxygen 0.04 and 0.2, sulfur. If you go through sulfur, relative abundance with respect to that percentage is very poor, 0.78 and 4.4. 4.4, remember, M+2 peak, M+2 contributor sulfur only 4.4. Okay, that values you need to remember in order to calculate number of carbons, number of halogens. Some selective groups carry 2 halogens, 3 halogens or 4 halogens. The data is mandatory. So everyone try to practice the data which I given. You work out in your rough paper. Keep working that particular data questions. So the data questions are most important. So the data questions actually we'll discuss in your next class. But if you want to do any data question regarding mass spectra, you need to know the relative abundance of heavy isotope with respect to light isotope. Okay. So hope you understand this isotopic ion concept as well as even electron as well as odd electron ion concept. Okay. So remaining part we will discuss in your next class. In your next class you will see how M+1 peak helpful to calculate number of carbons, how M+2 peak helpful to calculate number of carbons, then how binomial expansion used in calculation of isotopic peaks. Okay. So we'll stop here and we'll continue in your next class. Thank you.